Hi, I'm here with Karsten yet again, and we've got the Audi Quattro Lunar Rover, and we're going to talk electronics.
Yeah.
Excellent, because you are the senior electronics, you're the head of electronics development.
Exactly. Yeah.
For the whole project.
Yeah. Yeah. Exactly. So I've been doing the electronics for the rover for quite a while now.
Got it. But you've also been involved in lots of the mechanical
Yes.
stuff as well. We're pretty generalists, aren't we? Us electronics guys. So
Yeah.
Awesome. All right. What's the processor? Everyone's going to ask. What processor's driving this thing?
Yeah. So the interesting thing is, in the beginning we had like a central FPGA, like it was a Virtex 5 with a Power PC on it, and then we ran into some problems because. If you have a central processor and then we had also central motor drivers, which meant that we were driving high currents over long distances, and this led to some problems. And so with the new Audi Lunar Quattro, we actually decided to go away from this concept, and we developed a more like distributed system. So this is what you can see here. Is this in this unit there's a motor and there's electronics actually sitting on top of it.
Yep, which we'll take a look at. We'll get a shot later of. Yep, we can. That's probably the only thing we can tear down at the moment. Sorry, but yeah, okay. So you got the drive electronics in here.
Yeah.
Yeah, and you were saying each wheel can operate autonomously.80.
So there's a processor in each of those.
Yep.
So there is a
Which
processor?
Here.
It's an Atmel.
It's an Atmel what?
Yeah. It's an 80 mega something.
For all you Atmel fanboys, are you scared about the new microchip buyout?
No.
Microchip buying them? No, they're still going to pay.
So there's a radiation section going on at Atmel, which is pretty strong.
Right. Okay.
And so we can take one of those.
Okay. Cool. So they'll be able to supply your parts, the radiation hardened parts, everything. Can you order any of their parts to order as radiation hardened?
No. So So the thing is that radiation is very interesting.
We'll talk about that in a separate video.
So it's not like stuff doesn't work magically, and it's not like you don't need to have a certificate to be able to run it. Yep. But there is some gradually differences between them.
Got it. And so we've got a processor in each wheel, and there's one main processor in the thing. Is that it? Which one's that?
So that's there's a Smart Fusion 2, which is it's an FPGA with a Cortex M3.
Yep.
And there's also the onboard computing unit, which is this is in the lander. Sorry.
Right.
So in the lander we have another computer which is taking the control of the spacecraft. Yep. Which is more suited for the radiation environment.
In terms of the mission, once the lander lands on the moon, it's done, its job's done, and it just dies, and the rover takes over.
Yeah, essentially.
Right. But so the lander, it has its own power source.
Yeah.
It's not solar powered.
It's solar powered. Yeah.
Oh, it's still solar powered.
Everything's solar powered.
Everything's still solar.
Yeah.
Right.
In space, it's the easiest way to get. I was asking about those radio heaters, and it gets tricky with the paperwork.
Thermoelectric generators. Thermoelectric power generators is the correct term. I'm going to get there eventually. So too much paperwork?
It was funny. I was at a conference, and opposite was the guy that is responsible for the new radioisotope generators. And I asked him how much paperwork it would be for us to launch it, and he said "Oh, that's a very good question. You should write me an email." But I'm afraid I don't want to go on the blacklist anyway, so I didn't bother. But he said that it would be in the order of 20 to 30 million paperwork to get it launched on a rocket.
Wow. Really?
Yeah. It's
20 or 30 million just to ensure that it doesn't fall on some city and the city gets
exactly
polluted. Wow. Okay.
Yeah.
So you're going. What battery solution are you going with?
So actually, we are just testing some of the regular lithium iron batteries.
I would have thought you'd go for a more hardy battery than the lithium iron. I thought the temperature swings would be too much for the.
Yes. So if you would put it on the surface of the moon, then the temperature would be too high.
Right.
But if you look at the rover, it's designed in a very peculiar way. It's sitting up because we want to have the ground clearance, obviously.
Of course.
But we also, if you look at the soil, it has about a temperature of about 100 degrees Celsius when we are landing.
Yep.
And
that's because the sun's hitting it. And
yeah.
on the dark, where there's no sun,
it goes freezing down to minus 180 degrees Celsius, which is why our mission only lasts one lunar day, right?
Right.
Because this is very difficult.
And how long's the lunar day?
It's about 14 days.
It's about 14.
Yeah, it's a half a month.
You're right. Yes, of course. And right, but what if you land in? There's no hills nearby that can shade. What if you accidentally landed in next to a,
we try to avoid that.
Right. Okay. Yeah. But that could be a potential screw up if you land in the wrong spot and shady and whoops.
There are many screw ups, and this is one of them. Yes.
Right. Okay. So there is no backup. You have to have the sun to power it when you land.
Yeah.
Right.
So I mean, so we have battery power that can drive it for about 2 hours.
Yep.
Which is sufficient to drive the 500 meters.
Right. Yeah.
But, right. we're not thinking about the 500 meters.
No.
If we only would drive 500 meters, we would be very disappointed.
Right.
Even though this would be a huge success, if you look at it from a
you land there, the whole crowd cheers, and
But we would be very sad about it. And one of our sponsors probably as well.
Right. Okay. God, that bloody Audi Quattro is crap. It only goes 500 meters and breaks down. Yeah. Right.
Need to avoid that one.
Got it. So why those particular, back to the processors, electronics, why those processors? Because you're the head electronics guy and that's what you like. What are the requirements that drive that?
So the thing is that sometimes it's really just what you like. It's on the main processor that we had in the previous generation, there was actually QNX running on it because I like QNX.
Right.
Why I don't like VxWorks, as I found out. But
we won't go there. Okay.
Yeah, it's like but Atmel for example, has a good reputation in the space industry.
Okay.
And because it's making space hard processors as well.
Right.
And for the Smart Fusion too, it's because it's a flash-based FPGA, so you don't have the problems with bit flipping stuff, at least not in the configuration area.
Sure.
And so there's radiation reports for every part they bring out, and so you can read out all the data. You can see how it does in a radiation environment, and this is critical for what we are doing.
Oh, excellent! Right. Yeah. Okay, but there were endless choices though.
Yeah.
That you could have chose.
I mean, the thing is that. You can choose from any components you want, but you have to judge what the risk of using that particular component is. Mostly this is constrained by the radiation environment. So you don't want to use something where you have zero data about the radiation, or you need to run a test campaign about it. For example, the MSP430 is those FERAM, for example, which is inherently radiation hard in some way. So that's, for example, interesting.
Yeah, right.
But the particular tests of the devices didn't show up so well. So and then you're like, oh, this is a nice technology and should be nice, and then you figure out actually it's not that good, and there's a lot of experience in there.
Let's talk about the energy of this thing. How much power does it use?
Yeah. So
how much battery storage does it have? How fast does it charge? Can you live with lunar dust on the cells? Will that be a problem when you land if it kicks up enough dust? And will these cells get covered and you're screwed?
Well,
what's going on?
So there were a lot of questions.
Questions.
So let's start at the beginning. So the solar cells that you can see here can produce about 93 watts.
93 watts
in the space environment.
Yep.
Because you don't have the atmosphere.
Of course.
So you have about 1,357 watts per square meter.
Which if people don't know, on land here in best case condition, normally 1,000 watts per square meter. So you get 1,300.
Yeah.
Sweet.
So that's
so it's automatically
a nice increase. Yeah.
Yep.
And so this power then is used to charge the battery in principle. And the battery is about 250 watt hours.
Okay.
And is mostly used for the motors, because you have those spikes and you cannot absorb them.
No, you've got to have a low ESR to drive.
Yeah, exactly.
Yeah. Got it.
So essentially that's architecture. We're trying to charge the battery constantly and use the energy that's available for the driving.
Got it. How much power does the electronics take?
Well, so it's about 30 watts when we're not doing anything. So you can charge with about 60 watts if we are not doing anything. The peak energy consumption actually for driving like uphill at the worst conditions actually not significantly more than the 90 watts actually we're taking.
Okay, interesting. Could you do this without having the tiltable solar panels?
Yeah, so the question is really just how much pauses do you need to take?
So, okay, to let it charge back up and then drive again, but you could continuously charge. You could continuously drive.
So we are aiming at the ability to continuously drive.
Yep.
This is what we really want to do. You have a continuous stream of video,
yep.
24/7 for the 11.5 days, and
as somebody goes, yeehaw, as I'm controlling because it's almost real time. We're talking about a second and a half, so 3 seconds total delay. You mentioned how you're going to do that. Can you explain how you're going to do that? You're going to have a 3 second buffer in there. What's
so it's probably not as much as it's more like oh,
and then right.
It's the basic idea, for example, dealing with the 3 second delay is that you use the stereoscopic images to build a 3D scenery, and then you project a virtual rover into that and hope that the actual rover is following your projection. This would be one way of dealing with it, because the problem is you're not seeing the rover from the outside as you're seeing it when you're driving, remotely on Earth.
Yeah, of course.
But you only have the vision of your camera head, and it can turn, but it will do with a 3 second delay, and so this is quite some challenge. Yeah. So you see your actual camera, but you see when you're starting, you see a virtual rover driving 3 seconds.
Oh, you'll see a virtual rover driving 3 seconds ahead.
Yeah.
Right.
But this is really just like a driving assistance that you have.
Right.
In the end, people are asking us why is the rover so slow?
Yeah.
And the 3 second delay is actually the answer, because we could drive 50 kilometers per hour, but with a 3 second delay you don't want to do that.
No, you're just going to slam into Apollo 17.
Yeah, exactly.
You're in trouble.
Should be avoided.
So you think you've got the energy problem licked?
Yeah. So this was the funny thing is that the energy was actually the one driving thing that got us from growing. So
I was going to say, because you started out shoebox size, right?
Exactly.
And you just you did the numbers on the back of an envelope.
Kind of, yeah.
Literally, you just went, can't work.
Yeah,
can't do what we want.
So it's not completely impossible.
Right.
So it depends on the architecture that you have. For example, if you say, okay, the lander is a relay, so then you can use like a Bluetooth connection, which is very low power.
Yep.
But the problem is that when you have a Bluetooth connection, you cannot go very far.
Exactly.
Right?
Yep.
And so we wanted to have something that's really useful and not just to win the money, but useful in doing exploration.
Yep.
And so we want to have something that can communicate to Earth directly, and this is why we need to have more energy.
How far into the process did you decide that was the only way forward, that you had to have a rover that could transmit directly back?
That was actually pretty early on.
Pretty early on, you came to that conclusion.
So the second generation is already pointed at this direction.
Okay, right. Yeah. But the first generation was what?
Yeah, the first generation was very optimistic. Let's put it this way. But I wasn't in charge of the electronics then, so maybe that's
right. It was a couple of hobby motors with a little frame.
Actually, no, it was already quite some nice motors. Right. Yeah, but it never drove, unfortunately.
Right. Got it.
The second generation was the first one I was driving.
Right. So this, which generation is this?
So this is the fourth generation.
Fourth generation. How different from the third generation one?
Not much actually. So the third generation was almost the same size. The wheels were 20% smaller.
Yep.
But overall, really no big change. It's just that there was a reason we called the former generation the tank.
Right.
So it was a little sturdier, and a little bit more functional looking.
Right.
So this one definitely looks more
This
sleek.
one is sexy, I've got to admit. Even lights up blue on the front. Yeah. That's just...
that was cheap to have.
Yeah. A couple of blue LEDs never goes astray, right?
Yeah. It's actually RGB. I can remote control.
Oh, you can... So you're sitting back in the control room remote. Oh, I think we need some red on the front now.
Yeah, pink looks pretty freaky.
Audience is getting a bit bored, the worldwide audience. So let's just... That's sad. Engineers.
Yeah. We will not send that to the moon, by the way. Right.
Right. So is it one big board in here that does everything, or?
Yeah. So this is one of the things that that we thought about a lot, especially in the beginning. So in the beginning, we anticipated to have a concept where we had one backplane and where we plug different
plug-in
cards
modules,
into.
and that's engineers always go the modular. They think, oh yeah, that'll be a good solution.
Yeah, the thing is that
why is it not?
It is a medium good solution. I mean,
right? Yeah,
you can test each component on your own, which is a nice addition to it. So and also production wise, it's not horrible, you know. You can but having a PCB of this size with connectors on it, it's like we were like,
in connectors, you got vibration, you got contact issues.
Yeah, so now we decided that we have cards, which plug in there, which are CubeSat size, which helps us to.
That's right. You were saying you've designed this around CubeSat.
Yeah.
CubeSat size technology.
Exactly.
Tell us why.
So the thing is that in the space industry, the CubeSat community is growing ever bigger, and if you want to do something on the cheap, the CubeSat community is probably providing you something. For example, radios. There are a great number of radios that we can actually use, which are CubeSat size.
So you will use like an off-the-shelf radio?
Yes.
Oh, okay, great.
Yeah.
Great. So you don't have to roll your own solution.
Yeah, no, developing a radio is not an easy task.
No, of course.
So buying that off the shelf is probably a good idea.
Right. What other modules can you get?
Well, actually, the radio is about the only part that we're buying.
That's where it stops.
Yeah. Okay. We do all our own electronics. So everything is really custom made for everything. Yeah, we are. So this is something that we started to develop very early on. We started with it in 2010. We started to develop our own PCBs, and ever since we just went ahead with it. And I think
it's not hard to lay out boards. It's not hard to lay out boards in the scheme of building a rover.
Well,
a board is not.
It's one board.
Tell us, is it rocket science?
One board, in isolation on your lab works pretty well, right? But eventually, you have to think about EMC, for example, which gets funky.
Why do you have to think about EMC?
Well, not because of regulations.
Right, and this is what I'm going to say, because I come from the marine electronics background, where you didn't care about that. It's in the middle of the ocean. You don't care about how much you radiate, or it just wasn't a problem. So why is it? Yeah,
but for example,
not a problem yet it is.
For example, in the beginning, we had a central motor driver unit.
Exactly.
And those are very high current on inductance, and they get into everything you do.
They do.
And this can lead to some issues, and so this is something that we learned where you have to take care of.
That's why they're out here.
Yeah, exactly.
That's one of the reasons. It just gets rid of your problems. Yep. And the other's inside a metal cage in there, and
exactly. So the other thing is that so the reason for having the modular like this is also because you need to have some thermal pass for it to get rid of the heat, because you're in vacuum.
I've got it.
You can't just plug in a heat fan.
Because now you were saying before, the thermal side of things, we've got 120 watts. 120 degrees C.
Infrared radiation from the bottom.
From the bottom, 120 degrees C, effectively, cooking the bottom of this. Yep. So when the panel tilts this way, the electronics can cool out this side. Is that the way to... Because there is no breeze.
Exactly.
Right? There's nothing. How are you coupling the internal heat out to the body, for example? Because that's it. Otherwise, it'll just cook inside, won't it?
Exactly.
You won't be able to... Oh, no, it can thermally radiate from inside to the walls and then to the outside.
Exactly.
But it's not as nicely. Is that what you're relying on?
No, this is actually... Okay. So, no, we're not just relying on it by accident.
Right, no,
but we're actually thermally engineering it such a way that the thermal conductivity is conducted to this side.
Yep.
And not to this side, which is the bottom part.
Oh, the bottom,
for example, because this is where you get all the infrared, right?
You get all the infrared.
And there's some thermal insulation gold foil happening on the bottom part.
Got it.
And some infrared radiation away to the black space on this side.
So there's a very specific reason why it's shaped like that in there.
Exactly.
This side it gets hot. This side you use to cool.
Exactly.
Because this is facing the
this is
lunar
going
surface.
to space.
This is going to space. It's shaded by the other one. Brilliant.
Yeah.
When did you figure that out into the design process?
Oh boy. Yeah. Actually, our second generation already had kind of the tunnel, as we call it, but it wasn't, really thermally designed in such a way. But in the second generation, we actually were like, let's place all the electronics below the solar panel, which is not a good idea.
Interesting. So we've got a 90-watt panel on this puppy.
Yeah.
We've got lithium-ion storage. I'm still surprised at the lithium-ion. Can that handle the temperature extremes? Because this is not a thermally regulated environment inside there, is it? Is there insulation? Is there thermal insulation that helps?
So the thing is that that this part, so you have the angle part, this part, and you have this part here, and this is where the batteries are sitting, which is the coldest part.
Okay.
So it will not get anywhere near 70 degrees. So it will be 60 degrees probably.
Right, because the lithium-ion batteries are exothermic; they heat up.
Yeah.
So you don't. So cooler is.
Yeah, but the thing is that, for example, we this is why we are running test campaigns with those batteries. For example, we the runaway is happening. If you pack them closely to each other, then the heat goes to the other cells, and then you get a runaway with all the cells. But if you put them into like a metal casing, for example, and attach it to a thermal control surface, then you can control how much the runaway you can kind of contain it to, so to speak, and prevent that.
Interesting. Thermals are a big thing. Yeah. Space electronics is a lot of thermals.
Yeah, so one of the things, for example, about the lander is it's flying in what's called the barbecue mode, which is
it rotates until such time as it gets close to the surface, then it orients then lands properly.
The barbecue mode is really cool. It's really the space term for it. I find it funny. Is that you hit one side, and because it changes, and because the other side gets very cold, and so you have to rotate try to even it out.
If people don't know, that's why when they went to the moon, you see in the movies, they rotate, the capsule rotates. It's got a slow rotation.
Also use some spin stabilization happening.
Oh, it's in spin stabilization, but it's so it doesn't bake.
Yep. Yeah. This is one of the reasons,
Awesome. So, you reckon you got all the thermal problems licked? No problems with thermal expansion of metals and stuff like that?
Yeah.
Panels? The panels are space rated, right? So you don't... Right, so
but the summer thing is that why we are only talking about 11.5 days of emission is because when the temperature goes from the plus 120 degrees Celsius, it goes down to minus 180 degrees Celsius.
At night, after
exactly.
lunar night.
Lunar night, yeah. And so the thing is that while the mechanics of dealing with that, well, not easy but known. The electronics part is very tough to do. You have all the components, and we are using off-the-shelf components, and then the bonding goes boom, traces break and stuff like this. So we are not expecting to be alive on the next lunar day, unfortunately.
But has anyone calculated? There's a 2% chance it might. I don't know. Cross your fingers, and
Yeah, you can always pray.
Right? Yeah, that's going to work. So. Engineers don't pray. They calculate. Yes. Do statistics.
Yeah, but the thing is, you can, if you go to a manufacturer like, how is this component rated for minus 180 degrees Celsius? You're like, what?
No.
Yeah. It's very difficult to get it to get a vacuum chamber down to minus 180 degrees Celsius because you cannot just throw it into liquid nitrogen, for example, which is an entirely different test.
Have you been able to simulate the environmental conditions? Have you been able to do it?
It's easy to go down to minus 60, for example.
Oh, yeah, of course. Yep, you can get the regular thermal ovens,
exactly.
Industrial ones.
So this is some of the tests we do. We recycle the electronics up to 100 degrees and minus 60 degrees.
But below that, you can't. So you can't really simulate the minus 180 that it would get during the night. No.
Would be very hard.
Right. Got it. Oh, it's going to die on the surface.
What a shame.
Not. The only way, well, maybe not. But the only way to get around that would be to have a thermoelectric generator in there, because it's nuclear. It would last
the thing is
50 years or whatever, and continuously generate heat. You could keep everything warm and.
Yeah, the thing is that people ask us, why don't you use as a big battery to heat it up?
Exactly.
But the problem is that our design is specifically designed to get rid of as much heat as possible. Which is exactly the opposite of what you want to do if you want to survive the lunar night, right?
And you can't win.
Yeah, it's very difficult to win. It's not impossible,
right?
But very difficult.
And it would screw up your mission requirements and everything else if you went. If you took that seriously as a requirement, that we really want a good chance of surviving that. That cold period, which lasts for 15 days.
Yeah.
Right.
Yeah.
So
the thing is that if you this is why, for example, the space agency missions get significantly more expensive than our mission is, because we say, well, we have 14 days of fun and then we are dead, know, and
that's it.
But if you say you want to have longer mission durations, then you need to account for that and do more engineering and more mass means bigger rocket, and this is why the mission to the moon from the space agency costs 600 million instead of 30 million.
Presumably you have to land on the start of the the sun cycle. A little bit later, otherwise there's not enough.
Well, so no, the thing is that the reason why you want to land on the beginning of the lunar day is because you need some shadows to see where the craters are.
Oh, okay, so you've got an camera imaging system in the lander that
exactly,
and because you need contrast, right? You need that light dark contrast to get the depth.
And but in the beginning of the day, the shadows are extremely long, and it's very difficult. But also the temperature is too low. This is another thing. But so you need to land in about the second or third day of the lunar day cycle.
Interesting. Right. Okay. So you've only got 12. That's why you've only got 10 days or something.
11 and a half days.
11 and a half days is what you're aiming at. You have bodged on. I'm calling you out. You'll see this in the unboxing video. I noticed this straight away. It's a $2 eBay headlamp, hot snotted onto the front of your $1 million Lunar Rover.
Yeah, the Audi designers were going probably to kill me, but
they haven't seen it yet.
No.
Yes, I wouldn't show it.
But we're not going to show the public, do we?
No, we're only going to show my 350,000 subscribers. Sorry, but why do you need a light on the front?
Yeah, so we were doing some testing where we wanted to see if the light is helping with the driving and if we had partially shaded areas.
Okay.
But it's
so have you got like a simulated lunar
so this environment? Is in Berlin we're actually currently building a 10 by 20 meters test bed where we can actually drive our Lunar Rover on. And
you got studio lights set up. You can simulate different conditions and as the
that would be nice, but you can do some envelope calculation on what kind of lamp you need to do a proper lunar illumination with 1,357 watts per square meter. So that's about 200 square meter. No, so we have a flat light coming from the top with LEDs, and it's about studio light. It's a shame honestly, but everything else would be like driving the cost to infinity and beyond.
Is the electronics a big deal in this? How many lines of code? How many, what's the hardest part of doing this? I mean, presumably the electronics is like, we could just do that. Kind of. Is it a given that the electronics is gonna?
So the thing is, I would say the hardest part about electronics is the integration of the multiple components. So so you have on your lab bench you have one motor driver with one motor. And on your lab power supply, right? Yeah. And you drive it, and it works perfectly. And then you have 8 of those, and you start to turn left and go full speed at the same time with all 8 motors, and then stuff gets very interesting. Then it really checks your power design, and this is where I would say the hardest part is really the power supply design, actually.
Okay, interesting. How you're not using any one-hung low-brand caps in there. How do you design a space power supply?
Yeah, so the interesting part is that you, so for example, if you cannot just use any capacitor you find, So the electrolyte capacitors,
they have a liquid in them.
They have a liquid in them.
Oops, so they can freeze. They can freeze.
Yeah, but the hardest part is actually because if you're driving them in vacuum, then they escape. It boils off and.
Okay. But they're sealed. They're hermetically sealed to a point.
Yeah.
Because they're a pressure vessel as well. They're
not well enough to be just using it.
Right.
So there are some hermetically sealed capacitors, actually, some of them which you are using.
Yep.
But you buy, so one capacitor is about 50 to 200 euros. And you don't want to have...
That's nothing for a capacitor.
You don't want to have too many of those, right?
Right.
So you're probably going with a tantal or ceramic capacitors.
Right.
So for example, if you're on our PCB that you see, we actually mostly have ceramic capacitors because of that.
Okay.
Because those are pretty safe. And also from a vibration point of view, if you have components that are standing off too high, the vibration is...
the vibration. Tell us about the vibration testing in this, because that's a big deal. I've had a lot of experience vibration testing electronics, and parts you never think would vibrate off. You hit the resonant point on the board and boom, it just pops off. Have you had any failures? Testing? How many?
So far, we're quite good actually. So,
okay, right. So you thought about it, because you knew you were going to. You're in about the most rugged environment.
Yeah, and also the PCBs itself are mostly small.
Right.
So if you have bigger ones, then you're running into the resonance problems that you're talking about.
Of the entire warpage. If you don't support the board in the middle, it can hit a resonant point. It's got a lower resonant frequency, and it can.
And also they because we need to be thermally attaching to all these components. You also have those dampening points. So.
Got it. Would you pot your boards? Encase them in a
putty
that's a lot of rugged environments will do that. Military environments, they will just we don't care about vibration because we're going to pour our goo in. It's going to set hard and nothing's going to vibrate off. Is that something you've looked into, or
so that's
because you can get the rock hard ones. You can get the rock hard ones, or you can get gel silicon gel ones that are re-enterable. So you can repair things and then fill them back up. And did you look into potting?
Yeah, we looked into some of those. You also want to. The thing is, as I told you, in vacuum, so you don't have any conductivity going on, so you need to convection going on, so you need to thermally connected. So this is why. So
you can get thermally encapsulate materials as well.
Yeah, exactly. This is why those are, for example, interesting for some of our applications.
Are you using those thermally conductive?
We are.
Stuff?
This is something where we currently investigating what we need to do. Yeah.
Right. Okay. I worked on a military thing once where we hermetically sealed the can, filled it with a nitrogen, I think it was, and nitrogen's a very good heat conductor, so it would conduct the heat from the core board out to the metal case and things like that, and it got tricky. It was
Yeah, but then you need to seal it, which is
you need to seal it, and we had to
yeah.
buy a whole machine that would actually sniff the seal to make sure there's no leaks, and horrible.
Yeah.
So this is don't go there. Tell us about the camera.
Yeah, so the camera is pretty neat. So
it's got 3 eyes.
Exactly. So we have 2 wide-angle cameras, which are used for driving. Those are actually color sensors.
Yep.
It's debatable whether you need color.
I was going to say, why, but they come as color, so
yeah. Right. So we can also, if you we can look at the at Earth. Which is pretty neat.
Okay. Yes. Yeah. You want an Earthrise shot, kind of.
Yeah. Also, so we have the middle one is a black and white sensor, and
you said it's got the filter.
Yeah, so it's a telelens, and it has a filter wheel in front of it, so that we can look at different wavelengths.
Right.
And it also allows us to make a gigapixel panorama of the surrounding.
Nice. Does it stitch that in camera, or does it send it back?
No, we do it on Earth.
Right.
It's it's pretty high detail because you have 2K by 2K.
Yeah, it's a 2K sensor.
Yeah.
And you said it can do 150 frames per second.
Well, yeah, it's
why?
It was a sensor that we found that is radiation hard and serves our purposes.
Okay.
And it can do 100 frames per second,
Awesome.
We would be driving pretty fast to need that, but
yeah, exactly. But but can your hardware sustain that? Can it get the data out that quick? No, I was going to say
no. We are aiming at 15 frames per second.
right. Okay.
Yeah, so
and how are you processing that in an FPGA?
Yep. So
okay.
we have an FPGA, and then it goes by Ethernet to further processing. Image
goes via Ethernet.
Yeah.
You've got Ethernet link inside this thing.
Yeah.
That's interesting. Why?
Mostly because it's easy to debug. So
yeah, of course.
This is
a separate module. You can debug anywhere.
This is one of the reasons that you. When you're dealing with space stuff, you can use always the space stuff, but if you're using the space stuff, it's expensive.
Yeah, exactly.
And so we are aiming at technology that is easy to use on Earth, because then if you use something that's easy to use, it will be tested. And the more testing you have, the better your confidence is in being reliable.
Exactly.
You know, and so you don't want to do the funky stuff and do the stuff that works. You know, and Ethernet is a very good solution because
it's been around for 40
and
years
you can talk to it in any operating system, and it's very well supported hardware wise.
Is there anything else on the Ethernet bus in there? Or is that
probably probably just the radio, the camera, and the image processing.
Oh, okay. You're not buying like a little hub from the $2 store, are you?
No,
I didn't think so. Right.
There is something fancy going on, but we have there's some switches that you can use.
So you've got one main camera which is 2K. What?
The other ones are 2K
resolution?
By 2K as well.
They're 2K.
Yeah.
So are they all the same?
They are all the same, essentially. Yeah. From an electronic point of view, they are all the same, because the thing is that one of the things that is very important, you know, for us is to have enough time for testing. And if you use different
cameras, you got to write all these interfaces,
you have to test them all the time.
Exactly.
And so we are looking to reuse as much as possible.
Yep.
And so we have actually we have 3 cameras there, and one camera which is sitting at the bottom, which is not in this rover right now.
Right.
That is for hazard detection, so that you can. It's a fisheye, so that you can look at all the wheels.
I was going to say you need a real big wide angle.
Yeah, this is something that we, for example, found out with driving around with this one. That you know, it's very difficult to judge what you're doing if you can't see the wheels. So, and this was one of the things that helped us tremendously.
Now, this is not an autonomous rover. Cannot operate autonomously. If you guys can't talk to it, it's dead in the water. Yeah, and does nothing. Right.
Yeah. Yeah.
So, was that ever a design decision?
Yeah, mostly. Yeah, the thing is that autonomy is great, but it's also computationally quite expensive. So one of the constraints is from an energy perspective, which results in a thermal constraint, which results in a mass constraint, and then so essentially we were deciding that that we cannot sustain autonomy. Except for maybe as a test, but not a real time autonomy that is pretty fancy, but something simple, for example.
Any accelerometers or anything else fancy in this?
Of course, there are many temperature sensors, and have an IMU, which is a gyro and accelerometer, 3 axis.
And what's that used for? Well, you have to know the rover's tilt.
This is really
slope of
exactly. This is really mostly for the feedback for the user, because we were talking to Gene Cernan, who was at Apollo 17.
Yes,
and he told us that the most difficult thing is to judge whether you're going up or down.
Interesting.
This. So this is something that's very important to know if you're going down a slope, for example. And but unfortunately, magnetometers are quite useless.
Right. Yeah. And of course, there is no magnetic field.
And the most fancy sensor we're actually having is an audio.
Oh.
Yeah.
Really?
So we have we're recording the body audio.
The body.
So we are touching a microphone to the body, so that we can hear the
clunk, 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 clunk. Okay, because it obviously doesn't transmit through the air, but it'll transmit through the chassis.
Exactly.
Right.
And this is so this is like a acoustic debugging aid, so to know what's going on in the rover.
I don't think we don't have that audio from the such clunk, clunk, clunk from the rovers in the moon missions.
No.
No, I don't think they had any audio at all. I think it was just video, wasn't it?
Yeah.
It was just video of them going. Yeah, they had a camera
and the radio
and
the radio hub.
And the radio, but that was it.
Yeah.
So that'll be really cool.
Yeah.
Clunk, clunk. Oh, that'll be hilarious.
Yeah, and then you can hear the moment it breaks.
When you can hear the moment when somebody's screwed up. Lock the door. FPGAs galore, because you're an FPGA guy, you're an FPGA fanboy. He's written his own FPGA controller language.
It's a language, yeah.
Briefly tell us about it, because this is the electronics video, so...
Yeah, exactly. So this is, it's called the Plain Simple Hardware Description Language, which...
What's the acronym? Plain...
PSHDL.
PSHDL, yep.
Yeah, so it's aimed at students that want to get into programming FPGAs, and... It's aimed at people that don't want to suffer from the pain that VHDL or Verilog provides you with.
They're not easy, are they?
No.
VHDL and Verilog are just...
The thing is that programming FPGAs is not easy, and PSHDL just makes it ever so slightly less painful.
What's the pain point that you're overcoming?
First of all, the concept. So people are coming from a software development point of view.
A sequential programming
and then
background.
you have one statement, and they execute it in order. And which in an FPGA, you are describing a network of registers which are connected with each other, and you need to.
You need to think about clocks and synchronous clocking and.
Yeah, and you need to like temporal folding of signals that get delayed and this round trip and stuff. So it's a big challenge, and also the languages. For example, VHDL, they are so many trap for young players, as you call them.
Yep.
It's unbearable.
It's terrible.
It's just and also the tools are slow. They crash a lot.
Yep.
So I'm aiming at PSHDL. I'm very proud that it's actually not as academic but it's it just crashes as often as the commercial tools.
Got it.
So I'm very proud of that.
Awesome. Can people download this?
Yeah, you can go to pshdl.org. There is actually an online IDE. You can get started. Awesome. And if you don't know what you want to do, you can go to waves.pshdl.org, which is a little game where you see some waveforms.
Right.
And you write some code and you need to match them. And
Too good. Thank you very much, Karsten, for the electronics. We'll do there's other videos. This is all part of a series, isn't it?
Is it?
Yes, a series of videos. We're going to probably talk about space stuff next.
Yes.
Awesome.
Let's do that.
And space electronics. So I'll link it in here. Catch you next time. Didn't have a look down here.
Oh, yeah.
At the motor.
So this is our motor drivers that is in here. What you can see is that we use those ceramic capacitors because the other ones are a bit tricky with electrolytes, for example. But you could use tantal, for example. That would work.
And you tried to conformally coat it?
Yeah, this was something we went like, oh, we need to go outside. Oh, it's a little bit wet, so I just sprayed something on. It's a body job.
Right.
But I hope it added to the protection.
All right, Karsten, we're gonna unbox a Lunar Rover. A Lunar Rover unboxing. Let's do it.
So, carefully.
Oh, carefully. Here we go. Oh, right.
Is it? No, wait.
No.
Wiggle a little bit.
Wiggle?
Go down a bit. Go down a bit. And
down a bit.
Wiggle a bit.
We're wiggling.
Yeah.
We're wiggling a Lunar Rover.